physical significance of divergence. So let us now understand the meaning for this divergence. What does it signify? As in gradient used to signify the normal direction given to the scalar function. So that gradient represents the maximum change. Here we are to see what does this divergence tell you. For that, what we are doing, we are taking the three axes, x-axis, y-axis and z-axis, and origin, and here we are assuming a parallelepiped, which is the 3D version of a rectangle, right, with edges as with edges having distances or length as delta x, delta y and delta z. That means it is very small, and these lengths, these sides, they are parallel to x, y and z axis respectively, right? So it is oriented in the direction of your coordinate axis. This is our assumption. Another assumption is that it is filled with some kind of fluid, right? So we assume that the fluid is moving from this left direction to the right direction, right? It is crossing this box. So we are saying the fluid is moving with the velocity v. It is entering with velocity v and it is leaving with velocity v. On this phase it is entering with velocity v, and on this phase it is exiting with velocity v. Okay, and the components are v1 I cap plus v2 j cap plus v3 k cap at the point p x y z. So we are assuming some point p here inside this parallelepiped. And now we have to determine, now the question here, the thing that we claim here is that divergence of v. What is v? V is the velocity of the fluid. So divergence of v give you the rate at which fluid is crossing a point per unit volume per unit time. So this is what divergence tell you actually, that how much fluid is crossing a particular point per unit time and per unit volume. So let us see how this is happening. For that, in order to determine this divergence, I'm saying let us first see, because I'm claiming here that it is the rate at which fluid is crossing a point per unit volume per unit time. So for that, let us see what is this total gain in volume per unit time. So total gain in volume per unit time could be broken down into three things. One is the gain in volume in x direction, then in y direction, and then in z direction, right? So let us see it one by one. For this x direction, let us see what is the case. So gain in volume per unit time in x direction, that would be equal to what? Here for x direction, what I'm saying this is my x-axis, right? So according to this axis here, I have two faces. One is behind this point P, this face, DCAF, right? This face, this, and one which is in front of this point P, right? So what is that face? That is this face B, C, H and G. So this is the face. Now, in order to determine how much volume is passing from here to here, right, in moving from this plane B, C, H, G to the plane A, D, E and F, right? So we'll see what is the difference. So we'll see how much volume of fluid crosses GHCB minus AFED, the two planes that I have told you, right? GHCB and AFED. So in order, so if we assume that at the point P, the velocity is given by V1 in the x component, so its component is V1. So accordingly, if we are taking this to be the back, this face of this parallelepiped, right? So according to this face, because we are moving in the negative x direction, so our velocity component would be subtracted here. So accordingly, we will have the value as for the from the phase that is behind the point P, for this phase, its value would be V1 minus the gradient of V1 in the x direction with a negative sign, because we are moving in the negative x direction. And for this plane, so we have this point P, one plane is behind this, one plane is in front of it. When you move from here to this plane in the negative x direction, so this is a x-axis, right? So this is negative x-axis, this is positive x-axis, so something like that. So here, for this GHCB plane, our velocity is increasing by this unit because we are taking the gradient of this vector V1 with respect to x in a positive sense, in a positive direction. So when you compute this, and moreover, this is the displacement in x, this is the displacement of velocity in x, and what are the we have to compute the volume. So for volume, we also require the sides y and z, and because there is no change in y and z when we move on onto these two planes, so that would not change at all. So its value come out to be this for in the x direction. Similarly, for the y direction, in this case, this is our y-axis, so that means this purple face here and this purple face here. And moving from this purple face to this purple face here, what is the change? So that change would be obtained similarly by this expression delta V2 by del V2 by del y, del x, del y and del z. Similarly, in z direction, it would be del V3 by del z, del x, del y, del z. Now you have three components. So what you can do, you can add up all these components and substitute the value here. So you will have the total gain in volume per unit time. What would be that? The addition of all these three. So when you add up all these three, you have this, and this is the total gain in volume per unit time. And if we are to calculate it per volume also, we have to divide by volume, total volume. And the total volume of Q would be the length in x, the length in y, the length in z, all multiplied together. So this quantity cancels out with this one. So you're left with this. And what is this? This is the divergence of the vector v, because you could write this to be del by del x I cap plus del by del y j cap plus del by del z k cap dot with the vector v1 I cap plus v2 j cap plus v3 k cap. So this is equivalent to this quantity, and this is this, right? So actually your divergence tell you how much is the gain in volume per unit time, per unit area of a particular fluid. So that is the meaning of divergence, right?